Hello, I'm Wei from Answer. Today I will be very happy to present you our recent work, Inducing Language-Agnostic Multilingual Repetitions. This is a joint work with Steffen, Johannes, Bjerva, and Isabelle Augenstein. There was a revolution in the multilingual community because of the huge contribution of multilingual encoders, such as m-BERT and Express. They feature more than hundreds of languages, and they are often scored in the first place on many NLP tasks. One of my favorite features is a zero-shot cross-lingual transfer because it allows for building cross-lingual NLP systems which are trained on English data only, but we can use the system to many other languages for which English data are not available. Let's look at the deficits of m-BERT and its friends. Intuitively, an NLP system trained on English generalizes very poorly to languages that are dissimilar to English, for example, Chinese. We justify these intuitions by this figure, where one point in the figure is a language, and then we see the languages in the red regions are the ones that are pretty similar to English, for which cross-lingual transfer from English perform very poorly. Another justification we made is for lower source languages. It's pretty clear to see that the languages that have least amount of data on Wikipedia, for which performance of cross-lingual transfer is also very bad. And to address these scarcity issues, we can use other augmentation techniques. This is exactly what XLM-R did. Of course, it achieves much better results than m-BERT, but it doubles the model size of m-BERT and involves much larger training data, and make the model very slow to train. So we raised the questions: how to keep the multilingual encoder lean and fast to train if we want to have a good performance of cross-lingual transfer to lower source languages and to dissimilar languages. To do so, we have to introduce a concept of language identities. We hypothesize language representations somehow preserve language-specific information, what we call language identities, and which could be implicitly learned from training data. We justify this by showing language embeddings in a two-dimensional vector space. As you can see, each circle in the figures is a representative embeddings per language, which we collect over a set of sentences obtained from Wikipedia. And each color means a language families. We see language representative embeddings in the same language families, in other words, with the same colors, lying pretty closely in a shared vector space. But the representative embeddings in different language families tend to be located very far from each other. This implies that it's very likely there exists language-specific information, namely language identity, somewhere in the multilingual representations, which leads to the big deviation of these representative embeddings in the vector space. In this work, we investigate two solutions: cross-lingual alignment and normalizations. And we found both solutions are quite helpful in terms of removing language identities, because language representations tend to be centered at the origin in a shared vector space. But we have to ask the questions: does removing language identities really helps? Which means, is it able to improve cross-lingual transfer for lower source languages and for languages that are dissimilar to English? Our answer is yes. By doing ablation tests over 19 languages and over 2 NLP tasks, we found both solutions are quite helpful, particularly for lower source languages and for languages that have lowest similarities with English. Now we can make a justified framings. We frame a task of improving cross-lingual transfer as a task of removing language identity. Now we will dive into our investigated solutions one by one. First is cross-lingual alignment. Indeed, this is a resource-intensive solution because it often involves up to 200 case parallel sentences from which we can use word translations using a word alignment tool such as FastAlign. Then we can frame these translations as cross-lingual supervisions, which we use to fine-tune multilingual encoders, such as m-BERT. Here is a concrete examples. We use FastAlign to extract word translations of German and English sentence pair. Then we get the word embeddings then we get their word embeddings from multilingual encoders. Then we use joint lines to minimize the distance of these encoders. The next solution we investigate is vector space normalizations, because we want to remove language-specific means and variances from multilingual representations. In such a way, representations of arbitrary languages will be centered at the origin of a shared vector space. To do so, we examine two ways, batch norm and layer norm, to induce such statistics, but I will skip the details of them. Instead, I will point out the difference of batch norm and the layer norm. Batch norm induce per batch statistics, which means the means and variance varied a lot across the choice of batch size. But layer norm induce statistics that are independent of batch size. In addition to vector space normalizations, we also provide the pilot study on test computations. The motivation is to decrease a linguistic gap between languages from computational typology point of view. For example, Romance languages frequently use prepositional contractions, mostly with articles and pronouns, for which English don't have. For example, in Germans, instead of writing fuel and das as two words, we prefer use a short version fuels in the formal writings, and this is not the case in English. So we have to remove contractions from German input sentences. And the second solution we investigated for test normalization is sentence reorderings, because languages often have different rules for the ordering of verb and adjectives. For example, in French, adjectives are often placed after nouns, and in German, verbs often appear in the last positions of a sentence. And both phenomena are not common in English. So to deal with them, we reverse the order of noun and adjectives for French, and we reverse the order of objects and verbs for German. Now let's look at the results of vector space normalization. And one thing we have to record is the difference of batch norm and layer norm. Batch norm is very sensitive to the choice of batch size, but this is not the case. But this is not the case for layer norm. The figure shows that the batch norm doesn't help at all, but the layer norm doesn't help at all, but the batch norm helps a lot, particularly when choosing a smaller batch size. We verified this in our setups over 19 languages and over 2 NLP tasks, but honestly, it's still unclear whether the smallest batch size leads to the best performance gains for arbitrary tasks. So we raised this question for future work. We think it might be useful to find normalizations which perform on par with batch norm, but is less sensitive to batch size. And then next point we investigate in this work is whether cross-lingual alignment and normalizations are complementary solutions. And the answer is yes. We found they are the best of friends because the combinations of joint alignment and the combination of cross-lingual alignment and batch normalizations largely outperforms individual solutions. But the one thing we have to point out is cross-lingual alignment leads to less consistent performance gains than batch normalization. For example, joint align. Joint align improve BERT encoder a lot, but it doesn't help for XLM-R roboter. We might think why this is the case. Since the differences between two encoders are pretty small, we suggest to look at the discriminative abilities of the encoders. To do so, we show the histograms of precise similarity between word translations and between random word pairs. And interestingly, we found XLM robots cannot distinguish them very much. And also, we found after alignment, XLM robots still cannot do so. But we also see batch normalization really helps. So we believe this is the reason why batch normalizations leads to much more consistent performance gains than cross-lingual alignment. And this will also raise another question for future work. We think it might be important to include random word pairs as negative examples when training cross-lingual alignment, particularly for XLM roboter. Next, we talk about the test normalizations. Let's start look at the results of removing contractions. In this case, we choose Romance languages because they frequently use contractions. And we saw removing contractions really helps, but the performance gains are not consistent across languages. And we also find the same stories for sentence reorderings. And we think the potential reasons for the shortcomings is the following. First, the occurrences of linguistic phenomena may vary across languages. For example, one dataset in Romance languages may include very little occurrences of contractions, for which the impact of removing contractions would be very small. The second is the pipelines that were used to generate linguistic features may induce errors. And the next point is we think test normalization is interesting, but it's a little difficult to scale to arbitrary languages because languages may have different linguistic phenomena. Our conclusion is the following. First, we show removing our language identity really helps and can improve cross-lingual transfer. And the second, we show don't forget to apply a simple batch normalization because it can rivals resource-intensive alignment and also leads to more consistent performance gains. And we also find alignment and batch normalization are best friends because they are complementary solutions. And also we found discriminative abilities of multilingual encoders may affect the robustness of alignment, and we suggest to improve the discriminative ability, particularly for XLM robota. Finally, we show that the test normalizations for arbitrary languages is a little difficult to design, which is still an open question for future research. We leave our code on GitHub, and you are more than welcome to have a look. Thank you very much.